with balancing, old school balancing. All right, next problem. A 15.67 gram sample of a hydrate of magnesium carbonate was heated without decomposing. So this is a hydrate problem to drive off the water. The mass was reduced to 7.58. What's the formula of the hydrate? So it's an empirical formula problem like we did the other day, going like describing what's going on with the reaction, with the heating of the hydrate. So 15.7 grams of magnesium carbonate. Let's scroll up and down. Can you guys read me the given so I don't have to keep scrolling up and down? 15.75?
6.7.
See. 6-7 grams of, give me the formula for magnesium carbonate, Jaylon.
You want the
Formula
molecules?
for
Formula for what? You cut out.
for magnesium carbonate in the problem.
Oh, MgCl3.
Yeah. The mass was reduced. All right, the mass was reduced to 7.58. All right, so the first mass is the hydrate. And so we're looking for what that X is in front of the water. And it says it's put on the heat and the water is evaporated off. So is the 7.58 the mass of the anhydrate, the waterless salt, or is that the amount of water that was driven off?
It's the amount of the waterless salt.
Right. Okay, so when we do our empirical formula problem, we'll take the salt and then we'll take the water. So what's the mass of the water?
8.09.
Okay. All right. Anybody have the mass of magnesium carbonate?
84.32.
Everybody agree with that? Okay. Divide 7.58 by 8432. Somebody else. Jake Robinson.
Could you repeat that, please?
Can you do this part of the problem, the 7.58 divided by 8432?
Mm-hmm.
Mr. Rica, I got 84.31.
31.
Wait, Mr. Rica,
Yep.
what could I give you the answer for it?
Jake's doing that for us.
Oh.
Did you guys put 8432 or 31?
32.
I put 32.
Okay.
I don't think it will matter.
Yeah, I was gonna say I don't think it's gonna matter in the problem, but some periodic tables, if you're not using my periodic table, round differently, or maybe you didn't round to 2 decimal places. So that's not really a big deal. On a task, I'd look at your work and see what your answer. I base the answer off your work. That would be fine. All right, Jake, do you have that answer for me?
I got 0.09 if you round it.
All right, I need 1, 2, 3 significant figures. So I need, besides that 0, I need 3 digits.
Well, I got 0.08989. So
8, 9. So 1,
Yeah.
2, 3. So 0, 8, 9. And then that's where we're going to cut it off. So 9.
okay.
All right. Okay. And the bottom one, Chris, you want to do the bottom one for me?
Yeah, I could do it.
So 8.09 divided by 18.025.
Yep.
I got 0.44882.
Right, we need 3 sig figs.
So 0.449.
49. Okay. Divide by small.
Wait, I'm pretty sure it's 0.449, not 0.0449.
Yeah, I also have
Yeah,
point
that's
four
what
four
I had.
nine.
I read it wrong. That's what I had. I had 0.449.
Maybe you said it right. Maybe I wrote it wrong. Thank you guys for stopping me. All right. How many times does that go? Let's see on my screen. Oh, there it is. Delay.
I rounded it to
What's the delay?
5.
Let me see. What's the exact number? 0.449 divided by 0.899. Oh yeah, 49944. So yeah, that's fine. That's close enough, right? It's 100th less. It's 6,000ths away from the whole number. All right, so what is the name of this hydrate? I almost called on Ryan Luckman because that name was in front of me. Nathan.
I didn't have a name. I just wrote that as my final answer.
Do you remember how we named it?
Oh, was it
So what,
the penta thing?
yeah. So you're going to say the magnesium. So this is what you're going to have to write on a task. So, pay attention to what I'm asking you for. Magnesium carbonate, pentahydrate. Okay. I see it. We're coming in slow on my screen. I wrote it a long time ago. It's still coming in on the screen. There we go. All right. Any questions with those problems? So that's what you're doing for your lab. So you're actually going to watch a video where they mass out a salt, a hydrate. They put it on the scale, give you the mass, you record it, and then they'll put it over a flame and they'll heat it up and evaporate the water off. And then you'll do an empirical formula problem. They're going to ask you specific questions along the way, like how many moles, when they say how many moles of salt do you have, then that would be this 0.80899. Those are moles. And then if they say how many moles of water do you have, and that would be the 0.449. Okay, so you're not just showing your work, they're asking you specific questions. Like I'm seeing this really long delay here. I don't know, it's really weird. Okay, so that's what the lab will be. It's just a couple questions. And then you'll have to name it. So just one of these problems. I feel like we're pretty good with these. All right, what else do we have to do? We need more empirical, or are you guys good with empirical and we move on to dilutions? I feel like we're going to need more time with dilutions. If I just post the key to the empirical. Anybody have any issues? Want to do an empirical formula problem? I mean, this is an empirical formula problem, but anybody want more practice? No? All right, let's do some dilutions. There will be a review tomorrow at 10 a.m. I'm not sure if I'm doing it or Mr. Ader is doing it, but if you actually if you have specific questions, maybe shoot me an email and let me know so I can plan ahead on which problems to have ready. All right. So on your weekly plan, there is the dilutions handout. It is under today's date. There's more hydrate problems, but I think if we run out of time, I'd rather spend time doing some more dilution problems. So when we go into lab, we'll have some kind of idea what's going on. So we did a few of these. I'm going to go ahead and start at the top again. I think we did 1 and 2 when we were together last, or when we did these problems last. So I'm going to start at number 3 and refresh your memory about molarity, and then we'll move on to the dilution problems that we're going to do in the lab. So what we're going to do in the lab is we're going to make a solution. So if we look at number 3, it says if 45 grams of calcium chloride are dissolved in 125.0 milliliters, what's the molarity of the solution? So to refresh your memory, molarity expresses concentration. Which is how strong or weak a solution is. We have a solute that's dissolved in a solvent, which is always water in our case here. The capital M is the symbol for molarity, and that's the number of moles per liter of solution. So that liter is actually going to count the solute that's dissolved in it. It's not just a liter of water, it's a liter, it's the whole amount of solution, including the salt that's dissolved in it. All right, so given we have 45.0 grams of calcium chloride. Anybody throw out the formula for calcium chloride?
CaCl2,
Yep.
I think.
Yep. +2 - 1. And it's dissolved in 125.0 milliliters. What's the molarity of the solution? So basically we have to fill in to get the molarity moles and liters. So we just have 2 conversions to do, and then we divide. So somebody's going to need to calculate here. We have 45.0 grams of CaCl2. We have to cancel out grams and go to moles. So we need the molar mass. Calcium's 40.08. I have that memorized. And chloride is 35.45. You guys all have your calculators down?
0.4055.
Wait, 40 plus 70.90.
Oh, my bad.
Oh, you got the final answer. You have the final answer?
That was the final answer. 110.98.
That sounds familiar. All right. Everybody knows where we got that. All right, what was the final answer then? Division?
You want 3 significant figures, correct?
Yes.
Okay, so 0.405.
Okay. Just looking to make sure that's reasonable. I'd like if 2 of you were actually doing the calculations just to back up the other person, because
I
Jacob's
got the
always.
same thing.
Okay, thank you. All right, so now molarity equals 0.405 moles per liter. And the number of liters, move the decimal 3 places to the left, 0.125. You don't ever have to show that work. I know you guys can just move the decimal 3 to the left or 3 to the right, depending on what you need.
3.24 molarity.
All right, so we would say we have a 3.24 molar calcium chloride solution. This is how we would write it. This is what we would say. 3.24 molar calcium chloride solution. That's how we actually say it. You know, that's the way we write it. All right, so what you're going to do when you go into the lab is you're going to have to determine how many grams, because we don't measure moles. You're going to have to make a solution, and I'm going to give you the molarity. Every group's going to have a different molarity, depending if we have enough for actually having 2 groups. You probably only have 2 groups. You'll have a different molarity, and you'll have to figure out how much salt do you have to put into a certain volume. And I'll tell you how much you're going to make, not necessarily a liter. Okay, probably 500 milliliters. So we have these special flasks. They're called volumetric flasks. This is important information for the next part too. So I'm actually going to take time to try to draw these. So there's this round flask. And it's kind of expensive because it doesn't have any markings except for one. It has one marking right about there that will either say 1 liter or it'll say 500 milliliters or 0.5 liters. So it's very specific. It's hand blown to exactly that amount. So that when you make a solution, you put the salt in and then you put the deionized water. We'll have to make sure we use deionized water. You put it in and fill it up to that mark. And once you get close, you use a pipette and you drop it in dropwise to have the perfect solution. Okay, because in chemistry, when we're doing quantitative experiments, we need to know exactly how much the calcium chloride is dissolved in that water. All right, and so when we purchase these chemicals, they frequently come with a very strong molarity, and they're already dissolved in water. So when Mr. Ader and I want to do a lab using a 0.1 molar solution, which is fairly weak, we might have to take a 12 molar solution and dilute it. And that's what these calculations are going to tell us how to do. The algebra is not all that difficult, but sometimes the concept of what's going on, because at the end, you kind of have to explain what was done. So let's take a look. Here's the equation that we're going to use for a dilution problem. M1, V1, so molarity and volume equals M2, V2. So we'll have two sets. So we're going to take maybe a strong solution. We call that the stock solution. And that's the strong one. And then we have a certain amount of it. What we normally need to figure out frequently is how much of that strong solution do we need to dilute in order to get the new solution that we're going to use in the lab. And say, I'll know I want 500 milliliters. That'll be enough for the. So we have 3 out of 4 variables, and we'll just have to solve for whichever variable we're missing. And then you'll have to tell me how much water I'm putting in to make it the amount of solution that we need. Okay, so let's look at a problem. How many milliliters of a 2.5 molar solution do you need to make 500 milliliters of a 0.10 molar solution? So the beauty of this equation, this algebra, you don't need to convert anything to liters. Okay, you can keep it in milliliters. Given. So how many milliliters what we're solving for? We have how many milliliters of a 2.5 molar solution. So the key here is to keep the given information paired up properly. So we need to specifically say what's M1, what's M2, what's V1, what's V2, and make sure we pair them properly. So I'm going to actually write M1, V1. Oops, I need some space. M2, V2. What time we got? You guys keep me on time here. Let me look at my watch. 11:12. We're good. So how many milliliters of a 2.5 molar solution? So that's a set. Do you need to make 500 milliliters of a 1.0 molar? So that's a set. So we just make sure we keep them together. 2.5. And they can go 1 or 2. It doesn't matter where you put it, as long as you keep them paired up. And it was 500 of a 1.0. Oops. Molar solution. Oops, B2. All right, look at me. Let's see how many sig figs we need there. 500 point. All right, we solve for V. One times 500 is 500, so 500 divided by 2.5. Have I got an answer? Two people. Jimmy could probably do this in his head.
200.
200. All right, what is it 200 of? What's the unit?
Milliliters.
Milliliters, because it's a volume and we started with milliliters, so we're ending with milliliters. Okay. All right, so what does this mean? So the question is, how much stock solution, how much of the strong solution that had a molarity of 2.5, how much of that, 200 is the amount of that, do we need to dilute in order to end up with 500 milliliters of a weaker solution, the 1.0 molar solution? We need 200 milliliters of the 2.5 molar solution. Now, when we put that into the volumetric flask, and we pick up a volumetric flask that has a 500 mark on it, we pour in 200 milliliters of the stock solution. How much water do we need to add? At this point, we have 300. So it's really, it's the best answer, I would accept 300, is about 300. Add about 300 milliliters of water. Because it's a weird phenomenon, but sometimes when you add water to something, add two things together, two liquids together, they don't exactly, like 200 plus 300 doesn't always make 500 in chemistry, because sometimes molecules slip in between one another real close, or sometimes they're a little bit more spaced out. So 300 is a fine answer. I will accept that, but just understand when you're doing this in college, in the lab, you're not, or in our lab on Monday, you're not going to take 300 milliliters of water and just dump it in. You're going to take a larger container, 500 milliliters, which is in your hand, and pour it into the volumetric flask and stop about a half an inch from the line. And then you're going to pipette drop-wise until you get to the 500 line. And what happens if you go over? You start over. Completely throw the whole thing away. You've screwed it up and you got to start from scratch. So it's really important in chemistry that you get that little detail. All right, it's kind of a pain, but that's pretty important. All right, number 2, time to check, 9 minutes. How many milliliters of water do you need to add? Oh, we already answered that. About 300 was the answer. C, to what volume should 1.19 milliliters of an 0.800 molar acetic acid solution be diluted in order to obtain a final solution of 1.50? Weird wording, but we can see that we have a set there. The volume 1.19 and the 8 are a set. And we're looking for the volume of the 1.50. So 1.19 and 8. This is called C. This was B. M1, B1. I can't remember. M2, B2. I know we were looking for B2. 8 molar and 1.50. Oops. Oh, wait, I forgot already. I really have hard times. Milliliters, 1.19 milliliters? I think that's supposed to be liters. 1.19 milliliters is a teeny tiny bit. Yeah, we'll just do it the way it is. What function? 1.19 milliliters, 8 molar. Maybe that's what we're going to put in there. Milliliters. And then 1.50. Yeah. All right, that makes sense. So we're taking a little bit of the strong stock solution. And one. All right, do some algebra. Eight times 1.19 divided by 150.
I got 6.35.
Same thing.
Same.
Okay. So that's saying that's what the total volume is going to be. So that's saying after you've added the water, that's how much. If you want a 1.50 molar solution, you'd have to have a volumetric flask that had a marking for 6.32. Not real practical, but the algebra and the concept is there. Time check. 5 minutes. Maybe do one more quick problem. Yep, that's an easy one. What volume of a 5.75 molar formic acid solution should be used? So there's one set to prepare 2.00 liters of a 0.1 molar formic acid solution. Why don't you guys read me the givens? So this is D. We are given a volume 1 and a molarity 1, and a volume 2 and a molarity 2. Jonah, give me one of those sets. Volume 1, molarity 1. One of them could be defined, doesn't matter. Oh, you don't have the problem open? Do you not have the problem open?
No, it's not right in front of me.
Okay, never mind, that doesn't help then. All right, so the volume is what we're looking for of a 5.75. Volume of a 5.75. And then we have 2 and 1 molarity. 2 liters, 1 molarity. One point oh. All right. All right, why don't you guys all try to solve this problem? So I do suggest that on a test you show a line of work. In case you get it wrong, you can get some partial credit. Because at this point, you probably could do it all on the calculator. First person gets a lollipop when we get back to school.
I got
Uh,
0.348.
Yes, who was that?
Jonah.
Yeah. There's a lag here too. I can't see moving. Yep, 0.348. Jonah gets a lollipop. Woo. Anybody else get that answer?
Yeah.
I got
I got
the
the same thing.
Good. All right, so not too bad, huh? The problem I think comes in when we start mixing all these problems. There's so many problems we've been doing. We thought we throw them all together. I think that's maybe what gives kids a hard time on this test. So we'll do, when one group is in the lab, the other group will do a test, a practice test, and then switch. And then the next day we'll do a big, one more day of review. So if you think at this point, these are all the problems, if you think you need some review already, then, those leaders, then come on Friday at 10 a.m. But do me a favor and email me because I'm not sure what kind of problems people are going to need to do. All right, I think my next class is coming in. We got to go. All right, check the weekly plan. There's a lab. Make sure you get that lab done, please. All right, see y'all later.
Thank you. Have a good day.
You too. I'll check that Zoom, Casey. I'm gonna go to that.